this lecture, we will analyze some of the amplifiers, and we will try to find the expression of or the amplitude of the IP3 and amplitude for 1 dB gain compression point. So this is the meaning of nonlinearity analysis. So we have seen that in general, an amplifier will be having this relation between output and input. So output is going to be of this form. So on and so forth. So this is going to be an infinite series. But when we try to analyze the behavior of amplifier for 1 dB gain compression point and IP3 point, we considered nonlinearity only up to of order 3. And we found that those expressions, the amplitude for IP3, that means the amplitude of the input for which IP3 point will occur, is given by this expression. So we see that it depends upon coefficient A1 and A3. And amplitude of the input for 1 dB gain compression point is given by this expression. So here again, we see that coefficient A1 and A3 appear. So if we have any amplifier, and if you want to theoretically find out what will be the AIIP3 or A1 dB, then we need to basically find out A1 and A3. So here we will see that there are actually two ways of finding these coefficients. So first is, of course, find the expression for output and expand it in terms of the input. As has been done here in equation 1. So this is one technique, and then compare this expanded expression with equation 1 to find A1 and A3. So this is one way of doing. And the second way of finding out A1 and A3 is by differentiating equation 1 with respect to x. So for example, if you want to find out this coefficient A1, then we can differentiate this equation 1 time with respect to x, and then set x is equal to 0, so that the other higher order terms, they become 0, and smaller order, they will anyway become 0 because of the differentiation. So for example, if you want to know A1, then this A1 will be given by derivative of output with respect to x at x is equal to 0. Similarly, if we want to know the A3, then we differentiate this expression 3 times, and in that case, what will happen is this will become independent of x. These will be 0. Higher terms, they will become 0 when we put x is equal to 0. So A3 will be given by 1 by 6, third derivative of y with respect to x evaluated at x is equal to 0. So these are the two techniques that we will follow to find out the expression for AIIP3 and A1DB. Now we will start with simplest scenario. So let us take a simple common source amplifier. And this we are going to consider without degeneration. So here we have a DC at the gate, source is grounded, so for biasing purpose, and here we are giving time varying input, which will be a sinusoidal. And we know that for common source case, the input quantity X is actually gate to source voltage. That means VGS. And output quantity, which we'll be calling Y, is the drain current. Right. And this drain current, of course, when it flows to a load, gives rise to voltage. So the primary output quantity is drain current. So in all the amplifier that we will analyze today, we will assume this drain current as the output quantity. And here we have kept the blocking capacitor to isolate this time varying, say let us call AC from this bias part, which is DC. So this ID is our output quantity Y. And here this output drain current will be decided by the total gate to source voltage, which, as you can see here, will have two components. One component DC contributed by this VB, and time varying component contributed by this input voltage. So in general, drain will also have these two components. So here the total gate to source voltage is going to be gate minus source voltage, which is so in this case, gate is connected to both DC and AC. So this VI is AC part and VB is DC part. Source is grounded in this case. So I'm using this capital subscript with small letter to designate quantity containing both time varying and constant, that means DC, and this capital for subscript, capital for a main symbol to designate DC quantity, and small subscript and small letter for AC quantity. So here we have both DC plus AC. So we know that the drain current is given by this expression. So this is the most widely used expression, but this is not the most accurate. This serves most of the purpose that we encounter in analysis or design. So GS we have already found out, and this is threshold voltage. This is a DC quantity. This is a small number. We will be designating this number by K. This will occur very often in this lecture. So this now becomes VGS we have already seen is AC plus DC minus VTH. So this becomes VI plus VB minus VTH whole square. This can now be expanded, and we will get, let me write first the DC quantity, VB minus VTH whole square plus 2 VB minus VTH into VI plus VI square. So this becomes K into VB minus VTH whole square. So this is going to be DC, completely constant term, independent of time. This is dependent upon time, and the second term is also going to be dependent upon time. So here we have expanded the output quantity, which is the drain current, and input quantity is this VI, and we can now compare this with the equation 1 to find out the constant. But here we can see that there is a no third order term. So term or non-linearity. So when we expand the well-known, most widely used expression for the drain current, we see that MOS apparently doesn't have a third order and higher order non-linearity. So this is because we started with a certain expression for the drain current. Now suppose we want to know that what is the third order non-linearity in this common source configuration, then we will have to take more accurate expression for the drain current. So that will reveal us that there is a third order nonlinearity present in the common source configuration. So that is one way. And the second way in which third order nonlinearity appears even with this simpler expression is if we go for the degenerated version of common source configuration. So there are two ways in which third order nonlinearity so one is taking more accurate expression for ID, and this is of course without degeneration. And second is, even with this simpler drain current equation that we took just now, if you go for degeneration, then we will see that third order nonlinearity appears. This equation we will call as 3. So even with equation 3, with degeneration, nonlinearity will appear. So first we will see that the more accurate expression for ID without going into the derivation aspect. We will simply pick it up and then see that how that leads to nonlinearity. So more accurate expression for ID is given by this expression. So this is what we have been taking, but if one wants to be more accurate, then there will be one more term in the denominator, which for the majority of cases can be taken as equal to 1. Here. So we see that we have in denominator 1 plus product of two factors. So we will be calling this as factor alpha and this entire thing as factor delta. And here now we have few more terms. For example, mu 0. This will be called as zero field mobility. We have V sat. This is saturation velocity of the carriers, and theta. This accounts for the effect of what is called vertical field. And L is channel length. And other quantities are known: threshold voltage and gate to source. So we will not see the detail of how this is derived, but we will take this and then try to see that how third order nonlinearity comes into picture. So this denominator term can be written as ID is equal to K into VGS minus VTH whole square divided by 1 plus delta. So we can take denominator to the numerator part for the expansion purpose. And this delta term is usually small, and that is why the equation 3 is used most of the time. This is quite small, smaller than less than 1. So that is why we need not include this denominator term all the time. Otherwise, this is the expression that we would have been using for the drain current. So since delta is small, so this term can be expanded, and we can neglect the higher terms of that expansion, and in that case this will become simply 1 minus delta. But in general, this expansion will have infinitely many terms. So we have overlooked all terms and included only the first order term here. This can be written as k into VGS minus VTH whole square, and we can now substitute delta, because ultimately we want to write this expression for ID in terms of VI so that we can compare with the equation 1 to find out the coefficients. So delta is alpha into VGS minus VTH. So the first term here is alpha multiplied with VGS minus TH. So here, let me emphasize that GS is time varying external input with the DC bias. So this is GS. So we can write ID as K into VI plus VB minus VTH whole square into 1 minus alpha VI plus VB minus VTH. So here we can call the DC part as overdrive voltage, just to make the expressions compact. So now you can see that we have VI here with second power ultimately, and VI here with first power, first order. So when you multiply, of course, VI now will have third order. The maximum power that will appear for VI is third power. But if we had taken a linear expression for expansion of this term, then we would have got the other order terms as well. But we are interested in P1 dB and IIP3, which depends upon the first and third order. So we have approximated the expansion of 1 plus delta raised power minus 1. Now here, when we do the expansion, we are going to get a DC term K into, there's going to be DC term. This whole thing is going to be DC. And then we will get K into, so I'm not writing the exact expression for all these terms because this is going to be linear. So we will get first order term, then we will get second order term, and then finally you will get third order term. So if you do the complete expansion, this is what you will get. Now, if you compare this expression after filling these expanded terms here with equation 1, what we will get is A1 as A into 2 minus 3 alpha VOD into VOD. So this is what we will get for A1. And when we compare the third order term, we are going to get this thing, right? So we now have A1 and A3. And we see that IIP3 and 1 dB both depend upon the ratio of A1 and A3. So let us define a quantity R as magnitude of ratio of A1 and A3, because this is what we will be encountering very often. So when we do this, what we get is 2 VOD minus 3 alpha VOD divided by alpha. So K cancels out and minus sign gets cancelled because of the magnitude. So therefore, the input amplitude for which IP3 occurs is given by 4 by 3 magnitude of A1 by A3 square root. So when we substitute this ratio and do the analysis expansion, we get 8 VOD by 3 alpha minus 4 VOD whole square. So note that this is a function of VOD. It depends upon VOD. And so one can ask what we should do for maximizing AIIP3. That means we want more larger and larger input amplitude for which this point occurs. That means we will now be able to use our amplifier for wider range of input. So to know the maximum of this thing, we need to know the maximum of this ratio. In other words, maximum of this R. So if we can find out the maximum of R, we can find the maximum of AIIP3. So for maximizing this, find the maximum of R with respect to VOD, of course. So we need to solve this equation, which gives rise to 2 by alpha minus 6 VOD is equal to 0. So this gives VOD is equal to 1 by 3 alpha. So we just need to confirm whether this VOD value will give indeed the maximum value, not the minimum. So we can just find out the second derivative. And this turns out to be negative. So that means this gives rise to maximum value, not the minimum. So for this case, for this value of VOD, we need to know what is the AIIP3 that we have derived here. Let us call this as equation 4. Or rather, this has 4 and this has 5. So we have equation 6 giving rise to the maximum value. So from this 6 and 5, we get AIIP3 max value as 2 by 3 alpha. Now this R also appears in the expression for 1 dB, which is 0.143 R. So in this case, the exact expression is this one. And if you want to maximize it, again, we see that this is a function of VOD, so we have to maximize. So maximizing this means maximizing R. So the same value of VOD, which gives rise to the maximum value of IP3, will also give rise to the maximum value of 1 dB. So a 1 dB max occurs for VOD is equal to 1 by 3 alpha. And this value is going to be 0.143 by 3 alpha. And alpha square, in fact. So this will turn out to be 0.22 by alpha. So this is the maximum value and for these two parameters. So we obtained these two parameters when we took more accurate expression for the drain current. Now we again get the nonlinearity, third order nonlinearity. Even if we start with a simpler and well-known expression for the drain current, but we take the degenerate case for the CS. So in this case, source is no longer grounded, rather it is connected to ground via resistor. So let us start with the well-known drain current equation, simple equation that we have been using. And see that when we degenerate, we get the third order nonlinearity. So here, this is only the gate voltage, not the gate to source. Now gate to source voltage is going to be a little bit involved. Earlier source was grounded. But now source is at certain voltage. So it is this gate to source which has to be kept into the expression for ID. So therefore ID now becomes A into Vi plus Vb minus, sorry, this is Rs. So here we have DC, and these two, they can be combined, and we will call it as OD. We have already defined this term. OD for overdrive voltage. So now here, from here, there are two ways in which we can proceed to find out the those coefficients. So first is this is, you can see that going to give rise a second order equation, quadratic equation. In ID, and independent variable here is going to be Vi. So solve this quadratic equation and find the expression for so solve this quadratic equation, find the expression for ID. This is going to be function of Vi, and this Vi will appear in a very complicated way under square root term, and then expand in terms of Vi. So this path is going to be more laborious, so we'll not follow this, but I'm just pointing out that this is one of the ways. So quadratic equation, find the expression, expand, and then of course compare with the uh, expression equation 1. To find A1 and A3. So this is going to be more tedious path. So we'll not take this route. Rather, we will take the route of differentiation. So we are going to differentiate it to find out the various coefficients. So we have seen that the first derivative gives rise to the A1 and the third derivative gives rise to A3. This equation 7. And this we will do with respect to the input, which is Vi. So let us first try to find out A1. So for this case, we do this differentiation. So we get 2K Vi minus Rs ID plus VOD into 1 minus Rs del ID by del Vi. Now this has to be evaluated at Vi. then only this will become A1, related to A1. So for Vi is equal to 0, so we write here VOD. So this term is there, this becomes 0 minus RS. And this time I am going to use a different symbol for this ID. I'm writing capital I with capital D. And then 1 minus RS del ID by del Vi with Vi is equal to 0. So here, this is important term. And why I have used capital ID? This capital ID is drain current only due to the DC gate voltage, that is VB. So this is a DC drain current. You can say the bias drain current that exists. So this factor actually is going to be equal to GM. So we know that DC drain current will also be given by this DC gate to source minus TH whole square. So GM is 2K VGS minus VTH. And it is this voltage that we have been calling as OD. So GM becomes 2A no, here there's going to be a slight difference. Not this is OD, rather here gate voltage is going to be PB, source is going to be RS, ID, and minus TH. So this is the expression for gate to source voltage. Now here, this VB minus VTH, this becomes OD. So 2K VOD minus RS ID. So that is why this expression is GM. So now we can solve this derivative equation for del ID by del Vi, and this will become GM 1 minus RS del ID by del Vi at Vi is equal to 0. So this is also, of course, at Vi is equal to 0. This becomes GM by 1 plus GM RS. And this we have seen is going to be equal to A1. And in this case, you can see it is positive. So we have found out the first coefficient. Similarly, now finding A3, this will involve a differentiation 3 times equation 7 3 times, and find del ID cube by del Vi cube for Vi is equal to 0. So once we solve for this, we can get the expression for A3. So when we solve for this quantity, this will turn out to be 6 times A3. And this, if you do, this is what you are going to get. So here you can see that if we make Rs is equal to 0, A3 becomes 0. And this is what we saw, that in common source, if there is no degeneration with the simple uh, expression for the drain current, there is a no third order nonlinearity. So A3 is minus 2 k square Rs by 1 plus Gm Rs raised power 5. And here we see that this is negative. So we saw that for these gain compression and other things, this A1 and A3, they are of opposite sign. So therefore, AIIP3 is, which is 4 by 3, A1 by A3, square root, becomes 2 Gm by 3 Rs, 1 plus Gm Rs whole square divided by K. And A1 dB will be 0.071 Gm Rs into 1 plus Gm Rs whole square by K. So these are the final expression for these two parameters. So these were the parameters for single-ended amplifiers. Now we will see that what happens when we go for the differential version. So CS amplifier is used in differential architecture in two different ways. In one way, we keep the uh, potential at the source of the MOS constant. Here. So source of both M1 and M2, they are fixed to, in this case, 0 voltage. So this is one way of using. And here the output quantity is going to be the difference of these two currents. So this is one configuration. And here we need to provide certain DC voltage at the gate of the MOS. In the second configuration, we allow the voltage at the source to vary depending upon the input, but we keep the total drain current constant. That is sum of the drain current flowing through two MOS as constant here. So here this voltage is not fixed to any specific value. This will be varying with the input. Additionally, here we need not provide any gate voltage. We can straightway feed our input, time varying input. And here also the output quantity is ID1 minus ID2. And this ISS, this will always be sum of ID1 plus ID2. So in the previous configuration, sum of ID1 and ID2 need not be fixed. ID1 plus ID2 not constant. But this voltage is constant, source voltage. Here source voltage is not constant. This can change, but the total current is constant. So this configuration is preferred because it is able to suppress effect of fluctuation in the any common gate signal present at the output. So now if we analyze these two configurations to find out the AIIP3 and A1DB, then we see that in the configuration 1, if you start with the simpler equation for the drain current, then there will be no third order nonlinearity, because here there is no degeneration, and we have seen that in simple common source configuration, third order nonlinearity occurs in two ways. Either we take more accurate expression for ID, or we go for the degeneration. So here there is no degeneration, and if you take the simple expression for ID, there will be no third order nonlinearity in this configuration 1. However, in the configuration 2, even with the simpler expression for ID, that means ID as K VGS minus VTH whole square. So even with this expression, the configuration 2 gives rise to third order nonlinearity. For configuration 2, now let us try to find out what happens with this current equation. So here we know that the output quantity is ID1 minus ID2. So if one derives this expression, this will turn out to be K into VI 4 ISS by 2K minus VI square whole square root. So here VI is VI plus minus VI minus. So these are the time varying inputs, of course. And K we have defined. ISS is this bias current. So this we will be calling delta ID as K into VI. And here we can now take certain factor outside so that we can expand this square root term. So we take 2 ISS outside. So we take this factor, first factor here common outside, and then we get 1 minus VI square divided by 2 ISS by K 1 by 2. So here we can clearly see that when we expand this, there will be, of course, infinite many terms. So this is going to be infinite series, but what we will do, we will terminate it to only first order term. So this will be then approximated to AVI to ISS by K. In fact, we could have simplified this to write like this. And this will become 1 by 2 into VI square divided by 2 ISS by K. So this is after expanding and including only the first order term. We have neglected the second and higher order term in the expansion of this square root term. So here we can see that we get third order nonlinearity. So here there's one more thing to note. There's a no DC term and no second order. And this should not come as a surprise because we had already discussed that if you go for the differential architecture, that in the ideal situation, that means where both the halves of the circuit are identical, there will be no even order term in the output. So here, that is why we are not getting any DC and a second order term as well. So this is the advantage of a differential amplifier. Now we can compare this equation, which we'll be calling 8, with our original equation 1. So to get A1 as 2K ISS square root and A3 as minus 2K raised power 3 by 2 divided by 8 square root of ISS. So here we see that this is positive, this is negative. That means they are of opposite sign. Now this ratio A1 by A3 can be found out, which is 4 ISS by K Therefore, one can find out AIIP3 as 4 by 3, 4 ISS by K, which will finally simplify to 4 ISS by 3K. And A1 dB as 0.1434 ISS by K is equal to 0.572 ISS by K square root. So we see that whether the nonlinearity, higher or nonlinearity, it appears in any amplifier is dependent upon the amplifier architecture. For example, for this differential version, whether we are going for constant voltage version or constant current version, and whether there is a degeneration or whether there is no degeneration. And of course, all these are with respect to the simple expression for the drain current, which we use most of the time.